So here I am in my hotel in Thailand on holiday, but I've got a bit of a cold. So I thought I'd take the opportunity to write up a few pages of topical stuff to make a video for my YouTube. So let's get cracking. Concept. We use water as a heat transfer medium. With a specific heat capacity of 4,200 joules per litre, water is an ideal choice. A deep understanding of volumetric flow is essential for system designers of hydronic systems. In heating systems, energy is moved from the heat source to the emitter. Water is heated at the source and cooled at the emitter. The volume of water and the temperature rise or drop at either the source or emitter are the result of energy added or taken from the water. We use a simple formula to calculate this energy transfer. Now, some years ago, Adam Chapman and myself used to present a course for eco-technicians, and we presented it once with an engineer called Maurice Mudd, who, when he turned up, had presented the mass flow calculation as a triangle. And we really liked this, so we've named it the Maurice Mudd triangle, and we tried to stick to that name just for the idea. It works a similar way as the Ohm's law triangle. It's just a really simple way of writing out any kind of formula and making it easy to do the transposition without really understanding proper transposition. So anyway, Maurice Mudd first arranged this in a triangle similar to the Ohm's law triangle over 10 years ago, and so we call it the Maurice Mudd triangle today. And the Maurice Mudd triangle is simply the old, let me see if I camera, simply the old mass flow rate triangle that you've been used to seeing generally. So we're looking at the power in the top there, and on the bottom we've got the dt times specific heat capacity, and the answer is in litres per second. The flow is in litres per second. Now you can use kilowatts in the top there, and then change the joules to 4.2, and we know that the 4,200 is an approximation, not an exact number. So let's go back. Right, okay, so application. We're going to look at two systems. We're going to look at a boiler, 15 kilowatt output, delta T20, and an underfloor heating system of 15 kilowatts at delta T7. And I've deliberately selected a fixed return temperature for these examples to lead to a further point of learning further on through the video we're making. I've chosen 30 as the return temperature, in line with the standard design ideas of 50-30 design that commonly used to determine the output of your gas boiler. You'll see it on top of a Viessmann boiler, 50-30, and most of the design work I do is based around 50-30. And that's good for low temperature boilers. So at the boiler we've got a return of 30, flow of 50, so that's a delta T of 20. We've got 15 kilowatts, and if we stick it through our Maurice Mudd triangle, we're going to get to a flow rate of 0.179 litres per second. Now, on the underfloor heating system, we're going to have a return of 30. We're running at delta T7. So we've got delta T7, we're going to have power output of 15 kilowatts. So again, through the Maurice Mudd triangle, we're going to have a flow rate there of 0.510. And as 7 is approximately 7 is approximately 1/3 of 20. The flow rate at delta T7 is approximately 3 times the flow at delta T20. So we've got 0.179 versus 0.51. So considerably higher flow in the underfloor heating system, but they're both running at 15 kilowatts. Now also it might be worth noting at this point that the flow temperature at the underfloor is 37, and the flow temperature at the boiler is 50, when they both have a return temperature of 30. That's been quite deliberately picked for this. Right, skip a page. Right, so combining the systems. So we want to connect our underfloor to our gas boiler. We have an obvious issue, however, with the underfloor flow being 3 times greater than the boiler flow. We need a mechanism to allow these to be connected. A mixing valve can do this job for us. A 3-port mixing valve allows the full flow from the boiler to be mixed with 2/3 of the underfloor heating return flow. This creates a delta T of 20 across the boiler and delta T of 7 across the underfloor heating system when they're both running at 15 kilowatts. And from this example, we can establish a rule for our design criteria. And that rule is going to be that for underfloor directly connected to a heat source, the flow temperature needed for the correct delivery of energy is equal to the underfloor heating return temperature plus the delta T of the heat source. Now, I've done the heat source because it doesn't have to be a gas boiler, but if you talk in terms of a gas boiler, that the flow temperature from the boiler will be 20 degrees higher for a boiler at delta T 20 than the return temperature. So again, we had that return temperature of 30 from the underfloor heating, so our flow temperature from the boiler needs to be 50, but our flow temperature for the underfloor when they're mixed is only 37. And the reason for this whole thing is to point to the fact that, you know, people think of underfloor heating systems as being lower flow temperatures than the radiators, but in fact very often they can be higher. You could need the boiler to run at a higher temperature for the underfloor than it does for the radiator circuit. Right, so we can see that the flow temperature required at a modern condensing boiler can be unexpectedly high to an underfloor heating system. Hope that all makes sense. If we add a radiator circuit to our design and choose 50/30, we can match our boiler, radiators and underfloor to run at the same full load temperatures. This, however, will not function correctly at any other load, as the radiators and underfloor will follow different ratios between flow temperature and external temperature. So I talked about this a few times about the ratios. So weather comp curves are based on the idea of a ratio. This isn't strictly true, but it was something that a customer of mine who was a commercial controls engineer explained to me, and when I checked it out, it seemed to be a pretty accurate basis for working out weather comp curves. So basically the idea is that if you have a ratio, a common one of Eastman is 1.4, it's the default on the boiler. So for every 1 degree centigrade, the temperature outside becomes colder. The flow temperature to your radiators will rise by 1.4 degrees centigrade. So it's a very useful concept. It doesn't quite follow through. If you look at the heat curves from Viessmann and Vaillant, they don't quite add up to that. There's some other criteria going on, but as a base measurement, you can accept those ratios. So you can do a very good approximation of what the flow temperature of your boiler should be at any given internal to external delta T, depending on your curve, and you won't be far out. 3 or 4 degrees maybe, but not far out. Right, so at full load, we're going to have these systems running at the same flow temperature. This, however, will not function correctly at any other load, as the radiators and underfloor will follow different ratios between flow temp and external temperature, as we just discussed. Historically, we only designed for full load scenarios, but those days are long gone for good designers. So this is true. You know, on the old-fashioned systems, we only designed for full load, so -2, -3 external, and we did all our pump sizing, flow rates, and everything based on that information. And we weren't particularly worried about anything else. The boilers were all on, off, and oversized and everything anyway. So it's just a way of checking that at one temperature this thing was going to work reasonably well. But now with weather compensation, load compensation controls, and smart pumps and weather compensated pumps on the Viessmann, burner linked pumps on some of the boilers, constant pressure pumps, all the other type of pumping scenarios we get, things have become somewhat more complicated. So you need to understand the impact of your design at all sorts of loads, not just the design load. Okay, also these theoretically matched system in real life are not going to work to our design. And that's the case as well. The calculations are all brilliant, but they're never right. So the heat loss calculation is going to be slightly wrong, the flow rate calculation, there will be slight errors in everything. So when you put all this together, everything's going to be a little bit wrong. And but hopefully close enough. Right, so what happens when the flows and temperatures don't match the design? The results are undersupplies to our circuits, over or undersupplies to our circuits. Also, we may want different temperature and time on each circuit. For example, our underfloor at night is set back to 18 degrees from 20 degrees, but our radiators may be set back to 12 degrees. Some people have them set back as low as 3 degrees in the night time. And our circuit now, for sure, it's going to be that the underfloor heating system requires a higher temperature than the radiator system. So really we need to design around that. So we're going to need to use two mixers, not a single mixer. See lots of people doing Viessmann designs with underfloor on a mixer and the radiators not on a mixer. Now, if the pump's going to run on the radiator circuit, which it will do, you're going to have water delivered to that at the higher temperature than you want for the radiators, for sure, because you'll be running at the flow temperature it needs to generate to deliver the energy required to the underfloor heating system. So you're going to have a very warm night on your hands, and very unhappy customers as well. I've had this happen a few times. And also, where I've tried it with a single mixer on underfloor, I've had situations where, you know, you actually end up with the curve on the underfloor set higher than the curve on the radiators trying to compensate. I've had to go back and actually put the mixing valves on the radiator circuit rather than on the underfloor heating circuit to get the control needed to keep the radiator circuits cool enough. So now I just put the two on. In the Viessmann design guide as well, I've noticed in the copies I've got that they only actually give you diagrams for two mixers. They don't give you a diagram for a single mixer. But they do sell the sub-mount kits, and the sub-mount kits only have a mixer on the plate separated circuit, which is designed for the underfloor heating. So you've got to be really careful. They've got to make sure that your underfloor heating circuit is designed at a considerably lower temperature than your radiator circuit. Now you could do other design methods to compensate for this. You could use external controls and zone valves to actually shut down the flow, or maybe to cut off the pump that runs to the radiator circuit, but that isn't really how it's designed to work in the first place. And of course other systems might be running on zone valves and stuff anyway, so they won't notice the problem, but you're going to need to have Römstadt's internal sensing to run those other controls rather than just running on pure load compensation or weather compensation. And as you know, I like the Viessmann kit, so I want to be designing this to work with the correct flows to the correct circuits at the correct times, and do everything absolutely to the letter of the law. Right, so how do we design for this? Viessmann use variable temperature mixers, and as we can see from above, there will need to be a mixer on both circuits to be able to control the flow temps. Other manufacturers may use on-off options that use zone valves and room sensors to deal with mismatched flow rates. We can use hydraulic separation or isolation. And I use these terms to differentiate between plate heat exchanger isolation and close coupled T's, slow loss headers in the term of separation. These are not mainstream titles for those items. It's something that I've sort of tried to use to just indicate which one I'm looking at. So plate separation obviously gives total protection to the boiler from any contamination in the system. It's great for older systems, and Vaillant actually, I'm told, require plate separation on all of their bigger boilers. I'm not sure what the kilowattage is, but over a certain size they insist on plate separation, and that's I believe is to do with the ratio of volume of water in the system to the surface area of the heat exchanger. Excuse me. And they're looking there at the amount of contamination that will get deposited on the heat exchanger, probably just even in initial fire up. So plate separation just gives a completely different environment for your boiler and guarantees the boiler is going to stay pretty close to spotless. But I call that isolation rather than separation, and you can argue with me if you like, but it suits me to call it that, so I know what I'm talking about. Right, so why would we use different types of separation? So various reasons. We have insufficient residual pump head, so this is where the pump in the boiler has already overcome the resistance of our heat exchanger, but the amount of pump head that's left for the system is insufficient to service our index circuit, so we would use hydraulic separation so that we could use a second pump that wouldn't see the resistance of the boiler, and it would just be there to overcome the head loss of the system itself on the index circuit. System flow is greater than the boiler, the heat source, so where the system flow, a good example would be underfloor heating mixed with radiators. There could be a scenario during the heat up phase where the flows are really, really high on the secondary side, and we'd need hydraulic separation to allow the system to run at those higher flow temperatures, right? Higher flow rates. Then obviously the other one is where the system flow is less than the boiler. So it might not be possible to run the boiler low enough and could really have a very low load on the boiler. So we'd use hydraulic separation then as well, and that's mentioned on some Viessmann training course that I got some access to. Additional water mass is required, so again, systems with poor modulation on the boiler, or very, very tiny systems where we might require a bigger mass of water to help deal with cycling on it. Heat source protections, that's the plate separation I've already discussed. And the other one is multiple heat sources. So, you might have 2 or more boilers to connect together, and you would do those into one low loss header and then run your system separately downline of that low loss header. So for systems with underfloor heating and radiators, we're going to often need hydraulic separation to allow the system to run at different flows to our boiler. As our underfloor will often require higher boiler flow temperatures than our radiators and higher flow than the boiler, I tend to fit hydraulic separation to all systems with underfloor heating, but it isn't always required. Simply, I don't have the information available to calculate it as if it is required or not. So very often if you're in a retrofit situation, you don't really know the heat losses, don't really know the other things, but you pop in the hydraulic separation, plumb it all up, and everything works great, as it's nearly always needed. The chances of you putting it in unnecessarily are quite low, but of course it can be true. Right, change of rule. So anyway, once you fit hydraulic separation, the situation, the rule that we spoke about earlier, that changes. So once we fit hydraulic separation, our first rule becomes invalid, but it's useful to consider that it still suggests that our underfloor heating will often need higher flow temperatures than the radiators. With hydraulic separation, our rule changes to the delta T from the hydraulic separation to our underfloor heating system. Basically stated out, it's for underfloor heating downstream of a hydraulic separator, the flow temperature needed for the correct delivery of energy is equal to or greater than the underfloor heating return temperature plus the delta T between the secondary flow and return of the hydraulic separation. So I hope you followed that. So rather than the boiler now, it's the hydraulic separation. Boiler could be running at all sorts of different flow rates upline of the hydraulic separator. So then we're looking at load matching from here. Now, and basically this is where the boiler can see the system load, and it needs to be able to do that to load. So if a heat source can in effect see the system load, it will match that load. Not all boilers are equal, of course, and some have poor modulation, some of them have different control strategies. But in an ideal world, the boiler would just load match, sit there and tick over and give exactly the right amount of energy out that's required by the system. To see the load, the boiler must see the full flow and the temperature drop through the system. The boiler will have a set flow target temperature and will modulate or switch on and off to best achieve this. Weather or load compensation is designed to do this as accurately as possible. So, load matching cannot occur accurately if the boiler cannot see the correct flow or return temperature of a system. So let's look at when the boiler can't load match and some reasons why. This is always due to poor balance and poor flow control. Poor balancing of radiators or underfloor heating loops create either an underflow or an overflow in that circuit. And we've seen the effects of mixing circuits with different delta T's, and this is the same in practice. However, At least these circuits have a load and a flow rate. So, excuse me. Lost my space. Yes, okay. Circuits with an overflow will have a raised mean water temperature and so will output more heat than required, and so raise the load seen at the boiler. Circuits with underflow will have a reduced mean water temperature and so will output less than required. Don't be confused by the circuit with underflow having a lower return and yet a lower load, and this is often confusing for new designers. In fact, I've seen some fairly high-ranking people making the reverse claim to the truth on mass flow rate, where they see lower return temperatures and assume that the lower return temperature means that the system has given up more energy. And in fact, that isn't. It could be true, but it normally isn't true. Now, another issue is short circuits. A short circuit is a route for the flow with no load. So basically, if there's any route that the water can take, so it just short circuits back to the boiler, same as an electrical short circuit, no load on it. So in electrics, if you have a load on a circuit, you don't get a short circuit, you get some work done. Same thing with plumbing systems. If we have an open circuit that just allows a short circuit across the boiler, then it's going to cause a short circuit. Sorry. So right. So an example of this is fixed bypasses and incorrectly applied close coupled T's. So let's consider a boiler with underfloor heating and radiators. The installer has used close coupled T's at the underfloor manifold, not at the boiler. So we've got no hydraulic separation at the boiler. We've got the boiler pump operating the radiator circuit and supplying flow to the close coupled T at the underfloor heating manifold. Usually that's happening behind a zone valve, so I've written accordingly. So when the underfloor heating close coupled T is in circuit, the balancing of the system is changed. The boiler pump has now got to increase the flow to achieve the same head loss through the close coupled T short circuit as was needed by the radiator circuit to prevent underflow in the radiator circuit. That's a bit of a mouthful, but basically when you're balancing a system, what you're trying to do is make the pressure loss through each circuit appropriate to get the correct flow through it. And if you suddenly open up a circuit that allows massive overflow, then you're going to lose the pressure loss across the circuits that are already balanced, and so you're going to get underflows through those circuits. And this is what happens when you do the close coupled T's at the manifold. Basically, as soon as the zone valve opens, the boiler pump is going to see that short circuit. The water is just going to take the easiest path, so the flow in all the other circuits will be the flow that can be generated through those circuits at the same delta P as your newly introduced close coupled T. And so this new flow will create a large flow with no load, a short circuit. This has the effect of reducing delta T about the boiler target flow temperature, and it is seen as a raised return temperature. So arguments that you can't raise a return temperature is not quite, it depends which way you look at it, I guess. But basically, if you allow water to short circuit and you measure the return temperature rises. Now the boiler will modulate back because it sees a reduced load on the system, and it will modulate back to maintain the same flow temperature. But you now got a reduced delta T. So a reduced delta T implies a raised return. If the pump could do that, if it could actually modulate down to increase the flow through the close coupled T to get the same pressure loss as it previously did just through the radiator circuit, the system would be in balance, but you would have a vastly reduced delta T and so a lower efficiency at the boiler, but you wouldn't have an underflow in the radiators, just in effect an overflow in the system. Now, however, that's unlikely. It's much more likely that you're going to get an underflow through the radiators and an overflow through your short circuit. And in which case we're going to have a reduced delta T, reduced efficiency, and we're going to have a reduced output from the radiators. Now, the reduced underflow in the radiators is going to be seen as a reduced load on the system, and the boiler is going to load match. So where we had a system, what did we claim it to be earlier, 15 kilowatts for the radiators, now the radiators can only give out, I don't know, 5 kilowatts, and so the boiler will see that as a combination of the flow and the temperature drop, and the boiler will only load match to the 5 kilowatts. So yeah, so you've got an underperforming boiler and at lower efficiency. And that's really it. So it's fairly simple stuff, and the bits, the key points to sort of work on are the fact that we're going to need to use 2 mixers very often on systems with underfloor heating and radiators when we're using weather compensation or load compensation, and not in combination with some kind of on-off control system with zone valves. And also that where people think that they're going to run underfloor heating systems on gas boilers with very low flow temperatures, it's not necessarily the case. We're still using the same delta T20 to deliver the energy that we need to the underfloor heating system. So anyway, I hope those concepts help, and I hope I didn't ramble on too much and it's been clear enough. So any questions, please ask in the comments section, and be happy to answer. Good luck.